in which we have some information given, for example, the evaporator length, the condenser length, the adiabatic section length, and all that. And this also has a wicking structure which has got 2 layers of number 50 mesh. The mesh is made of copper. So these details we had seen in the last class, and the objective of this problem was to get the capillary sonic entrainment and boiling limits. So as I said in class, these things are best understood if you work out the details on your own, which we will do for a similar problem on Thursday. Okay. So for example, here delta P that you can get using capillary action, that value is calculated here. This is delta P capillary, and then this is the maximum value. Similarly for the other limit. Now we'll go to another topic, which is thermal resistance of various parts of the heat pipe. Now this is utilized to calculate temperature drop. Okay, so let's see how this goes and what is the purpose of this. So this is a figure in which you can see various resistances, thermal resistances that you get. So for example, if this is the heat source and this part is the heat pipe wick evaporator section, then between the outside environment and the wall of the heat pipe, there is an outside resistance of R1. So if there is convection happening, then this can be because of convection. Then we have R2, which is the resistance of the heat pipe wall. So after the wall, you have obviously the wick. So there is this wall which is often made of copper, or can be made of something else also. But next to the wall, you obviously have the wick, right? And next to the wick, as you go towards the center of the tube, center of the heat pipe, then you will see after the wick, you will get the vapor zone, right? These are the various layers. So this is outside resistance. This is the thermal resistance of the heat pipe wall. This is R3 is the thermal resistance of the wick structure, and R4 is the thermal resistance corresponding to the vapor liquid interface. So this is R4. And then there is an R5. This is because of the temperature drop that you get in the vapor column. Because in the central part of the heat pipe, there's this transfer of heat through the vapor layer. So that resistance is R5. And if you write these resistances in a slightly different notation, then we will get this. And then this is better. The previous figure was actually from some other book. This is the same thing. So there is a heat source, and then between the heat source and the pipe wall, you get an external resistance. So if there is convection, then this resistance will be like 1 over HA, that sort of thing. And then this is the pipe, this is the wick, this is the vapor space. There are 3 things, right? And the pipe resistance here is RPE. So RPE, E for evaporate. Correct. So we have similar resistance on this side also. This is RPC, C for condenser. And we also have resistance at the evaporator in the wick region, which is RWE, and this is an internal resistance in the evaporator section. This is RIE. This is the resistance because of this liquid vapor interface. Where is that interface? Interface is at the top of the wick, right? At the inner part of the wick. This is where you get this menisci. Right? The meniscus that you remember, the meniscus at the evaporator region. And there is a vapor resistance also, which we are calling RVA. Okay, so this is all that we have here. Now, if you can calculate the total resistance between the evaporator and the condenser, obviously that will help you calculate some temperature difference, right? That we know from thermal resistance. So, these are, this is the same figure and with the same notations, but this shows you some representative magnitudes of these resistances. Obviously, the values will depend on what kind of material you have, what liquid you're using, things like that. But these are representative values, order of magnitude. Okay. And the resistances are calculated using expressions like this, because we are assuming cylindrical geometry. So this sort of expression you're familiar with, right? So if you have a cylindrical shell, this is how you calculate the resistances. Okay, so this should not be difficult. Now, what is Kp, you think? Of the pipe material. Okay. So if it is copper, then use 400. Right, but you have RWE also. RWE is, again, think about the notation, W for wick, E for evaporate. So that resistance will depend on an effective thermal resistance of the wick. Sorry, effective thermal conductivity of the wick. So this K effective is an effective thermal conductivity of the wick. All right, so what is the thermal conductivity of the wick? The thermal conductivity of the wick will depend on the material of the wick and also the construction of the wick. But remember that the wick has liquid in it, right? It doesn't just have solids. So you can prepare a wick. Remember sintered metal, we talked about it a few classes back, but it can also be like meshes put together, like 2 or 3 meshes put together. So if you have, let's say, some meshes wrapped on one another, then it has got the metal of the mesh, but it also got the liquid in the spaces between those wires of the mesh, correct? So the liquid will saturate the space that is available to it. That's what we expect. So it will depend on the effective thermal conductivity of the wick, which we see, look at the cursor, that pointer that I have. So that shows the K effective. So that K effective will depend on the material of the screen that you're using, but also on the liquid thermal conductivity, right? So we have to keep this in mind. Now again, this table shows the order of magnitudes, and then let's go to this figure. We keep this figure in mind. So this is a circuit which has got some series connections, some parallel connections, right, of thermal resistance. Our interest is that we want to say something about the total thermal resistance of the heat pipe, correct? what is the benefit of being able to say something about the total thermal resistance? Actually, the benefit is that then you can say something about the heat flow. Correct? Because the temperature difference divided by the total thermal resistance will give you the heat flow. And that may be required, that you need to calculate at some stage when you are talking about heat pipes. Now, RPA and RWA, what are those? RPA is this resistance and RWA is this resistance. So why do we write this RPA thing? RPA, okay. P for this one, P for pipe, A for axial resistance. So we have RPA. Now that RPA turns out to be large. RWA also turns out to be large. RWA is the axial resistance in the wick. But how do I know? This is based on this kind of data. RPA and RWA have got 10 to the power plus something. Okay, typical values. These other things like this one as RWE and WC, this has got 10 to the power plus something. But these three, the first one and this, they have got 10 to the power minus some number. Okay. Now RPA and RWA are large. So this is large, this is large. So that means that the flow in this direction, flow in the axial direction, flow of heat will be small, right? So we can kind of say that heat flow will go like this. This path and this path, these are blocked. Okay. Now the other point is that RIE, RIC and RVA. So what are their values? RIE, RIC, C and RVA. Their values are like this. IE and IC 10 to the power minus 5, order of 10 to the power minus 5 resistances. And RVA resistance is of the order of 10 to the power minus 8. So these are actually very small numbers, right? So these resistances are small. If these resistances are small, these things are small, then we can actually just say that the total resistances are PE plus RWE plus RWC plus RPC. Correct? So we are saying that from here to here is kind of like not posing much resistance at all. Okay. So this is our total. So that's a good thing we have been able to simplify. So our total is RPE So why is RPE PA? RPA we said has got large value, RW has got large value. But why are we saying RPE is significant, RWE is significant? Okay, so RPA we are saying is large, correct? But what about RPE and RWE and RPC and RWC? These we are keeping, right? So they are in the reasonable range. 10 to the power minus 1. So this is not too large, not too small, right? But so RPE, if this is order of the order of 10 to the power minus 1, why is it that RPA is of the order of 10 to the power plus 2? Both are for the pipe material, right? You understand the question that I'm asking? Okay. What do you think? Of course, these are numbers I've got from table, but I'm just trying to understand why these numbers are like this. Why some of these numbers are large, some of these are small. Okay, RPA has much larger value of the length dimension, no? That heat flow has a much longer path, so the thermal resistance is higher. Whereas RPE or RPC, these just have to take place over a small thickness of the wick, right? Small thickness of the pipe, for example. I'm talking about this one, so pipe, talking about pipe. Okay, so we can have similar kind of arguments. So the axial distance, I mean, length is large, so the thermal resistance turns out to be. When you have more material, obviously resistance will be higher, correct? Okay, what about small value of RVA? RVA is of the order of 10 to the power minus 8. Why is it so small? So this is, it's getting quite a bit of length, but it's vapor, right? So you expect the thermal conductivity to be low. Yeah, so there is vapor getting generated in the evaporator section and then moving towards condenser section, but it's definitely vapor has much lower thermal conductivity, right? So that is 10 to the power minus 8. So I'm trying to give some reason for why we have arrived at this. So look at the individual values of the resistances and you should be able to say why this is large and why this is small, correct? We are not doing it blindly. Okay, so this is the convenient thing. Now, what else is there? We will also have some contact resistances. Let's say between the pipe and the wick, there will be some physical contact, right? So we'll have some contact resistance. Contact resistance is something which you have studied in undergraduate heat transfer, I'm sure. The contact is never perfect between two materials. You can see it there in the inset here. So contact is not perfect. There are air pockets and air has low thermal conductivity. So these things contribute to some contact resistance. Right. So this is something, the contact resistance is also something which we need to take into account when we want to calculate the total thermal resistance. The thermal resistance, our total expression that we saw on the previous slide, it was just RP plus RWE plus RPC plus RWC. That did not include contact resistance, but contact resistance needs to be included also. Okay, now just give it a couple of minutes to read this. You should know these sort of problems because we will be attempting these in Thursday's class. Thursday we'll do heat pipe, whatever problem is possible. So I'll ask you to do those in Thursday's class. And maybe something like this also. Heat pipe, we have already looked at one problem, correct? In class. Right? And this is the second one. First, just read this. copper water heat pipe and 6 centimeter long tube, and this is enclosed in a to cool an enclosed silicon casing. So there is a silicon casing in which this copper water heat pipe is placed. Then inner and outer diameters are given. Diameter of the vapor space, we called it D on D subscript V. So that is 4 mm. So this shows all the dimensions. This is the diameter of the vapor space. Okay, then this 5 and 6, and the lengths are 2 centimeter, 2 centimeter. This is also 2 centimeter, and the wick structure has 2 layers of 500 mesh copper screen. So the 500 mesh thing means that these meshes have got certain numbers. Okay, so 500 mesh will mean certain port size. Okay, right. What do we want to get? So some contact resistance is given between the heat pipe and the casing. So there's a casing in which you're placing the heat pipe. Condenser is immersed in a stream of liquid, and there is a convection heat transfer coefficient for that. The liquid is at 10 degrees Celsius and the heat pipe is operating at a transfer rate of 2 watts. So what is the temperature of the silicon casing? So we want to know the temperature of the silicon casing. So there's not much information given on the silicon casing, but apparently you're trying to transfer some heat. Okay? So there are things, these things are all given. These are the diameters. This is the wire diameter. Wire diameter corresponds to the mesh in the wick, the screen in the wick. Okay, and this is water thermal conductivity, this is copper thermal conductivity. And this is our total expression. We know this, and our total can also be written like this. Why? Because the evaporator and the condenser are physically like similar things, right? So we expect RPC and RP to be about the same, and RWE and RWC to be same also. So that's why we write this first expression. And RPE can be calculated using that usual relation for a cylindrical shell. Correct? So that should not be a problem. So we got this. And the RWE is given by this expression, and this has the diameter of the vapor space, okay, dV, which is given to be 4 mm. And our WE expression, as I mentioned a few minutes back, has a K effective, which is the thermal conductivity, effective thermal conductivity of the wick structure. Okay, so that is calculated as 1.205 watt per meter degree centigrade, K effective. So that value goes in here. So this gives you RWE as 1.474 degrees Celsius per watt. Now in this K effectiveness calculation, obviously there will be thermal conductivity of the wire, because this is a wick which has got the screens. So the screens are made up of wires. So the wire thermal conductivity will come into picture, but also remember wick has a liquid in it. So it also got liquid thermal conductivity. Epsilon is the quantity which is given by this expression, which has the geometry of this. So this has got this number N, which is 500 per inch. Okay, and this is from the given specification of the screen. Okay, 500 number is the specification of the screen. So we calculate epsilon, and this epsilon is used here to get this K effective. Okay, so our total using this formula will come out to be 2.956 degrees Celsius plus per watt. Now we are talking about this effective thermal conductivity calculation. You will see from here that it depends on the geometry, and these are the expressions. These expressions can be, these are based on some models. Okay, so you have this screen, wick made of screens, and then you can theorize it and you can make a model of this and you can write equations. But that part we will not do. We'll just pick this up from this particular table in the book. Okay. So these are expressions that you will be able to find in this book. This is wrapped screen that we are talking about. So we took this expression. There are others also, for example, packed sphere, rectangular grooves. This is sintered metal fibers, so something like this. Okay. So what have we got here? We have got our total, correct? But to get the heat flow, we're interested in the heat flow, and heat flow is given for this problem. Okay. Actually, we are interested in the silicon temperature, right? There is a silicon casing in which we are placing the heat pipe. What is given? The heat flow is given. Anybody remembers that? The heat pipe is operating at a heat transfer rate of 2 watts. So 2 watts is the heat flow Q. Okay, so this is what we write. So there is a silicon temperature which we want to estimate. Minus T infinity is the ambient temperature. And we have these 3 resistances at the bottom in the denominator. So which has got the heat pipe thermal resistance, our total, but it has also got this quantity. What's this? This must be a convection thermal resistance, and that comes from a heat transfer coefficient which is given. I think the liquid's heat, there's an external liquid, and for that the heat transfer coefficient was mentioned as 500. Okay, so this is H, this H. So this can be calculated, and this is the contact resistance that we are talking about between the silicon casing and the heat pipe. So this also has to be added. This we have already calculated. So this gives you a T silicon of 26.6. I don't know, he doesn't say whether this 26.6 is acceptable or it should have been lower. That's not discussed in the problem. Okay, that depends on the particular application that he has in mind. All right, so this is our discussion on heat pipe thermal resistance and how that heat pipe thermal resistance helps us calculate maybe some temperature, or if temperature was known, we could have calculated the heat flow, right? So these things are obtained like that. Now we'll spend a few minutes talking about the working fluid also. So you have a certain application in mind. What do you have in your hands? So you can choose maybe the material of the heat pipe, okay, the metal of the heat pipe, then the wick structure, and you also have to choose the liquid, plus of course the dimensions of the heat pipe. You know, what is the inner diameter, what is the outer diameter, what is the length of the heat pipe. These things all you have to decide as part of thermal design of the heat pipe. Right, so working fluid is one of the factors in there. So what working fluid do you choose? It will depend on the temperature at which it has to operate, how much heat it has to transfer, and things like that. So the typical operating temperature range is between the critical temperature and the triple state temperature of the working fluid. Okay, so these things are between the critical temperature and the triple state of the working fluid. Now this is another useful table. This is heat pipe working fluids. This is again, this information is available in Lee's book. He has taken it from some other book. That's why you see this number 21 here, which is a reference number. Now these are various fluids which are used in heat pipe applications. So this is melting point, this is boiling point. The useful range is between this and this. So water, for example, it's of course you know between 0 and 100, but the useful range is between 30 and 200. Okay, so you don't use water at 0 degrees Celsius in heat pipe. So this is some useful range. So this, obviously, you can see from these numbers that it depends on a lot of practical considerations. But as designers, we just refer to the table and pick up, okay, this is our application. Application is at roughly this temperature range. So which fluid will help us in that temperature range? Okay. So we would like to have a high value of surface tension. High value of surface tension is desirable for the liquid. Where is that sigma? We're talking about that sigma. Okay, sigma should be high because then you can do better capillary action, isn't it? You have to push the liquid from the condenser side back to the evaporator side. Okay, so high value of surface tension is desirable in order to enable the heat pipe to operate against gravity and to generate a high capillary driving force. And the working fluid should also wet the wick and the container material. Okay, so the contact angle must be very small because it has to wet the wick. And the working fluids used, can go from helium at 4 Kelvin to lithium at 2300 Kelvin. Ammonia can be used and things like that. There are a lot of heat pipes which are used in space applications. So low temperatures, very low temperature, isn't it? Space application. And okay, what are the desirable properties of the heat of the ideal fluid? It should have high surface tension to increase capillary piping, as I mentioned. It should also have high fluid density and latent heat of vaporization. Latent heat of vaporization, if it is high, then the mass flow rates will be lower, right? Because the heat that you are transferring is m dot times HFG, correct? If the HFG is high, then for a given heat transfer that you want, m dot can be smaller, then you have to handle a lower flow rate. Things like this. So based on all this, there is a figure of merit for these liquids for heat pipe applications, and they, this is calculated. This figure of merit is denoted by N subscript L, and it's defined as this thing. Now the figure of merit you can calculate, right? So you have sigma, surface tension coefficient, and then you can get HFG from tables. Mu L is the dynamic viscosity of the liquid, rho L is the density of the liquid. So these numbers you can get, and then you can calculate, right? Depending on the temperature that you have. So the figure of merit for various fluids are shown like this in this figure. So for example, you can see that if temperature is between like 300 to something like 300 to 500, water gives you a high value of figure of merit. Sodium is here, so sodium provides a high value of figure of merit, but this is also at high temperature. So sodium gives you a high value, but it's only at a high temperature. If you go to lower temperatures, the sodium figure of merit will drop. Okay, so this sort of thing one has already done this. So people have prepared this sort of plot, and they have got tables also. So we just use these. Now the important thing is that in the moderate temperature range, water appears to have the highest figure of merit. See, if you go to these sort of temperatures, then water is quite good. It's better than all these. Okay, so that's good news because water is obviously abundantly available, and something like this, if it has got a good figure of merit, then it's useful for us. You can, in many applications, you can just use water, not bothering about something else. Okay, so this is water is superior in this range, 350 to 500 Kelvin. And ammonia is good at slightly lower temperature. So water is from 350, he says. Okay. For slightly lower temperatures, ammonia can be also used. It's difficult to handle ammonia, so those issues have to be considered, right? So you can take a look at all these. This is kind of it's a bit descriptive, so you can look this up yourself. Now we'll spend a few minutes on the wick structure. We already discussed wick structure, and I had shown you photographs of wick, but these are some important points, 1, 2, and 3 regarding wick. So the wick has to provide flow passages which will help return the liquid back to the evaporator from the condenser, correct? And we need surface pores. So if you think about the wick, right, so this is the heat pipe and this is the pipe wall. Let's say this part is the wick, right? So it has got some surface pores and this has got some internal pores also, obviously, right? So the surface pores have to ensure that there is proper generation of capillary pressure. Okay, to understand this better, think about this, that on the evaporator side we get something like this. This is a, what's the name of this? Meniscus. Okay, and this side, on the condenser side, this looks more like this, isn't it? But this is the surface pore. This is the surface pore. Okay, and because liquid is evaporating so much from here, it tends to give you this sort of small radius of curvature, whereas here the radius of curvature becomes quite large. It becomes a flatter thing. So the job that the surface pores are doing is to create this difference so that the liquid can flow this way. All right, but there are internal pores also. So we have surface pores and there is also internal pores. And the other thing is, so the internal pores are important for the return of the condensed liquid. The first point, the liquid has to, through this the liquid has to move, right? Liquid doesn't move at the surface so much. It moves this way, like what I have shaded, moves through this one, goes back. So it needs the internal pore. It has to go like this. and there has to be a heat flow path between the container and the liquid vapor interface. So this is here is the liquid vapor interface, and this is the container wall. So between them there has to be transfer of heat also, isn't it? So there is a heat flow path also which goes like. Okay. And so the wick structure, an effective wick structure, let's see, maybe I can mark these things. So the effective wick structure requires small surface pores for large capillary pressure. Okay, so this has to be small, right, to give you large capillary pressure. Why? Why does it have to be small? Hmm? Correct, very good. So we had delta PCM, M for maximum. Okay, so this was you people are not revising at home, otherwise it should have been easier. 2 sigma cos theta by r. But since we are writing maximum, we'll write this as, okay, just this 2 sigma by r, which is what is r? R is this one. R is just this radius, correct? Radius of the pore. R is not the radius of curvature in this case. Right? Okay, so 2 sigma by r. So if you give small pore, then you are increasing the delta P that you can generate. Fine? Now we also need large internal pores in the direction normal to the liquid flow. What does it mean? Means the following, that okay, we have this thing. Let's say this is what I have drawn here. Let's say this thing is the wick, right? And the flow direction is, if the right hand side is condenser, left hand side is evaporator, then the flow direction is this, and normal to the flow direction means in this direction, right? In this direction you need to have large internal pores, otherwise you will create too much resistance for the liquid to flow. You are not responding. This is reasonable or not? See, the flow has to go like this. So if this here, the pores are very small, the internal pores are very small, then it will become more difficult for the liquid to move. Larger pressure drop, isn't it? But you want the liquid to move comfortably from the condenser side to the evaporator side. So the internal pores have to be large, right? Okay, I don't know why you're not saying much, because otherwise it's difficult to make out whether you are agreeing with what I'm saying or not. Disagreeing is fine, but then you have to say whether you agree or disagree. You have to say that, right? Okay. And also there may be, you need a highly conductive heat flow path across the wick thickness, right? So there is in this example that we saw, there's a silicon casing heat pipe inside, so there has to be transferred across the thickness, isn't it? So you need a conductive path, thermal conduction, heat conduction. Right, so these things you have seen twice or thrice. So You know this, and this is our wrapped screen. This is sintered metal. So these things are there. This is grooved, correct? And this wrapped screen wick is quite common. The example that we are looking at, there are like two screens which are wrapped, isn't it? Two 500 number screens which are wrapped. Now the surface pore size of this wick is inversely proportional to the mesh number. Okay, so 500 mesh will mean the pore size will be 1/500 inch. Correct? This is what we use in the problem also. And the flow resistance to the liquid flow. So you have these meshes, no? One mesh and next mesh. So if you change the if you want to change the distance between these two screens, you can tighten, right? Or loosen. You're wrapping two screens. If these two screens press hard against each other, then the internal flow direction, the pore will become smaller. Correct? And that is good or bad? Because the liquid flow will have trouble. Correct? Okay. So this is the sort of thinking that you should be able to do. That okay. Here, okay, so here one problem with the wick structure is that the temperature drop across this type of wick, when it is used for cryogenic or moderate temperature heat pipes, can be relatively large due to the heat flow path between the screen wires being interrupted by a liquid of low conductivity. Okay, so you can give large pore size by changing the tightening between the meshes, but then if internal pores are high, then it's also possible that because of a lot of liquid smoothly flowing, the thermal conductivity can be lower. Okay, thermal conductivity is higher if you have more wire, because it's more conductive than the liquid, isn't it? So let's say you're using copper screen, so the wires are very conductive. Sintered porous metal, that can be used. So pores of the sintered porous metal are usually small. So pores are small. You can see that from the photographs, like sintered metal, there will be very small pores. And they enable large capillary pumping pressure to be developed at the liquid vapor interface. But they will also cause small internal pores, which will result in large pressure drop when the liquid is flowing, right? Okay. There's also some discussion on actually grooved wick, but I think we are kind of running out of time. I will touch upon this a little bit on Wednesday's class, but we'll start something new also on Wednesday. The syllabus for the exam will be till heat pipes. Okay, but I would like to say that coming to Thursday's class will be, even though it's just the day before exam start, it's very important for you to come, because we will do heat pipe problems on Thursday. Okay, thank you.